In this problem, we're looking at a simple circuit where I have an ideal power source maintaining a potential difference of 3 volts, and the only other thing in the circuit is a 5.9 micro-Farad capacitor. In part A, we're asked to get the charge on this capacitor. So recall the definition of capacitance is how much charge you store per volt. So C is equal to Q over V. If we solve for Q real quick, this is how we find the charge on a known capacitance with a known potential difference. So I can write this as 5.9 microfarads multiplying 3.0 volts. And so farads times volts have got to give you coulombs. And I can just quickly write down the answer as 17.7 with this micro tagging along. That's a factor of 10 to the negative 6. So 17.7 microcoulombs, or in coulombs I could write it as 1.77 times 10 to the negative 5th coulombs. In part B, we're asked to get the energy stored in the capacitor. And our basic formula for energy in a capacitor is 1/2 CV squared. And again, we can just let that factor of 10 to the negative 6 tag along. And I get 26.6 microjoules. If we want to write this in terms of joules, that's 2.66 times 10 to the negative 5th joules. Finally, in part C, we get into the geometry of the capacitor, like how is this thing constructed. So it's made by foil strips that are separated by cellophane strips to prevent it from shorting out. The thickness of the cellophane is 0.155 millimeters, so that is the plate separation distance between the foil strips. Cellophane has a dielectric constant of about 7.2. And we should be able to find out the surface area of each of these foil strips in order to achieve a total capacitance of 5.9 microfarads. So what we're using here is the basic formula for the geometry of capacitance. I take that dielectric constant times epsilon 0 A over D. And we know the dielectric constant, epsilon 0 is the permittivity of free space, and we can look that up. And then we know the plate separation between the foil strips, and we know the capacitance. So A is the only unknown here. And I can write that symbolically as C times D over kappa epsilon 0. And then we just plug in. And my capacitance is 5.9 times 10 to the negative 6th farads. My separation distance between the foil strips is just the thickness of the cellophane insulator. That was written in millimeters, and I need to turn it into meters. So 0.000155. The dielectric constant kappa was 7.2, and then the permittivity of free space, that's 8.85 times 10 to the negative 12th farads per meter. And if I look at the units here, my farads are going to cancel, and then I have meters divided by 1 over meters, which gives me square meters, which is what I want for an area. And when I run the numbers on this, I get 14.4 square meters of surface area. So this can be achieved in real life by taking strips of foil that have a relatively small width, like on the order of centimeters, and an incredibly long length. Then the foil strips are stacked together with the cellophane strips and rolled up into a tight cylinder, and we can build this capacitor with a capacitance of 5.9 microfarads. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.